Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture Series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
It is my pleasure to introduce today's speaker, Professor Siddhartha Mishra from ETH Zürich. Siddhartha Mishra obtained his BSc from Utkal University in Orissa in the year 2000. In the same year, he enrolled in the joint integrated PhD program of IASC and TIFR. He wrote his PhD thesis on hyperbolic conservation laws under the guidance of Professor Adimurthy of TIFR Center, Bangalore. Since then, he has moved on to various aspects of applied mathematics, including numerical analysis, nonlinear partial differential equations, computational fluid dynamics, computational plasma physics, modeling and simulation in biology, etc. His research is mainly focused on designing computational methods that solve nonlinear partial differential equations arising in different areas, analyzing their effectiveness and designing algorithms to implement them. He has made significant contributions in these directions and is a world leader in the subject. He has been invited to speak in many prestigious scientific meetings, also has got many prestigious research grants. He has received many awards and recognitions for his research contributions. He was an invited speaker at the International Congress of Mathematicians in 2018, held at Rio, Brazil. He was awarded the prestigious Collage Prize of ICAM in the year 2019. Collage Prize is given by the International Council for Industrial and Applied Mathematics to individual scientists under 42 years of age for outstanding work on industrial and applied mathematics. He was also awarded the Infosys Prize in 2019. With this brief introduction, let me invite Siddharth to deliver his talk. The title of the talk is Deep Learning and Computations of PDES. Over to you, Siddharth.
Good morning, everyone. Welcome to this lecture where we're going to talk about deep learning and the computations of PDEs. So as all of you know, partial differential equations or PDEs are ubiquitous in science and engineering, and they model everything from the subatomic scale all the way to the galactic, the cosmic scale, with everything in between, such as the climate on Earth or how tissues shape and form. It's also well known that except in very special cases, you cannot solve PDEs explicitly in terms of solution formulas. So in order to simulate them or in order to predict phenomena with them, we have to use numerical methods. And a variety of numerical methods are there and have been developed for a long time. These include finite differences, it includes finite elements, finite volume, collocation methods, and many, many more. And these methods are extremely successful. However, there are some serious issues with these methods. And one such issue is the question of high dimensionality. In particular, if your PDE is high dimensional, then either it's too expensive or it's infeasible to use these numerical methods to compute solutions of PDEs. And by high dimensionality, I mean that the total dimension has to be greater than 4. Remember that space-time is 4-dimensional. So where do these high-dimensional PDEs come from? So you could have them in two types, or two varieties. One is the so-called explicitly high-dimensional PDEs. For instance, many people know in physics, you have the Boltzmann equation, which is 7-dimensional. The radiative transfer equation is also 7-dimensional. You have Black-Scholes equations from mathematical finance, Schrodinger's equation from chemistry, which can have hundreds to thousands of physical dimensions. So here the physical dimension is what is large or high. On the other hand, in this talk, we are going to focus on what are called implicitly high-dimensional PDEs or parametric PDEs. Now, where do these PDEs come from? So one source is from uncertainty quantification. So let's give you an example to begin with. So here, for instance, is a realization, a simulation of a compressible fluid flow or compressible gas flow. This is a single realization. So for a certain initial condition and for boundary conditions, this is what you obtain. Now, as you can see, there's a very complex simulation, a very complex structure with turbulence, with chaotic motion and so forth. And to do this, we require a highly optimized numerical code, something that runs on multi-GPUs, scales on multi-GPUs called ALSFIN, which has been developed in my research group. And even with that, for a single simulation on one of the most powerful supercomputers on Earth, PSDAINT, the most powerful supercomputer here in Switzerland, it takes about 300 node hours for a single run. It's a big run. It's 1024 cubed, which translates into about 1 trillion degrees of freedom. Nevertheless, it's 300 node hours, which is affordable. However, the object of interest is not a single sample, a single realization, because these are chaotic phenomena. So what you need are ensembles. So you need statistical quantities, such as the mean and the variance, and PDFs and so on. And this is precisely what falls under the rubric of uncertainty quantification. And to do this, you have to simulate this kind of a configuration, not once or twice, but hundreds or thousands of times. So even if you do this 500 times, the total cost, this being Switzerland, we can quantify things. It costs approximately $7,000 for a single ensemble simulation. Now imagine the number of scientific simulations that one can do and how expensive it is. So this is, these are the sort of problems which become almost infeasible on state-of-the-art high-performance computing platforms. Another example where parametric PDEs come in is an optimal design. So what one is interested in, so this is a sort of a cartoon for the actual physical problem. So you want to design a wing. So let's take a 2-dimensional cross-section, an airfoil, and you have compressible flow going around this airfoil or past this airfoil. And then what you're going to do is you want to optimize the shape of the airfoil in order to minimize the drag or optimize the lift to drag ratio, some objective function. So you have an optimization problem. So what one can do, or what one does in practice, is that you parameterize the shape in terms of some basis functions, something called Higgs-Henner functions. So it ends up being certain parameters, 20 or 50 parameters. And then for each of these parameters or each realization of these parameters, you have to simulate the PDE, compute the flow past the airfoil, compute the lift and the drag, put it in an optimization loop. And the bottom line, the punchline here is, again, we have to invoke the PDE solver hundreds or thousands of times. So the same story over and over again. That's why these kind of problems, they're called many query problems, because you have to query the PDE solver repeatedly. And remember that one call to the PDE solver can be expensive, but many of them, hundreds of them, can be prohibitively expensive. That's sort of the underlying problem here. So how do we do this? So one way we can do this is, remember that we have some parameters here. So an abstract PDE takes the following form. So this is some sort of a differential operator. You can think of the Laplacian, you can think of the operator that comes in the heat equation or Navier-Stokes. And your solution U is a function of space, X. This could be 3-dimensional or 2-dimensional. Time, of course, is 1-dimensional. And then you have parameters. So these parameters, for instance, could be the parameters that parameterize the shape of the airfoil. This could be 20 to 50. Or it could be the parameters which parameterize the initial conditions for this uncertainty quantification problem. This could be 50, let's say. That's a number here. So it's the parameters. The differential operator, of course, does not involve the parameter, but the solution does, and the inputs do. and this could be high dimensional. So this is how a high dimensional and implicitly high dimensional PDE arises. And our object of interest is for different values of these parameters, sometimes hundreds or thousands of values of these parameters, we want to compute the solution field, or we want to compute observables, quantities of interest, for instance, lift or drag, which can be expressed in this generic form. So now, as I told you, this is an expensive proposition. This can be prohibitively expensive. So what we're going to do is that we are going to replace the solution field or the observable, or we're going to approximate them by a surrogate. And the surrogate is going to be a deep neural network. This is the second part of my talk, deep learning. This comes in the guise of deep neural networks. Now, these days, deep neural networks are everywhere, omnipresent. They come in face recognition, in speech recognition, in recommendations from YouTube, in self-driving cars, even in protein folding, but they're increasingly being used in this context in scientific computing. So let me just revisit what deep neural networks are. So for my purposes, deep neural networks are just functions. So remember that we have a parameter y, a vector, which could be 20-dimensional, could be 50-dimensional, and my output could be a number or could be a field. It doesn't matter. Let's say it's a number. So since we're going to emulate that, we have functions. These are deep neural networks, but they have very specific structure. And the specific structure is that you have a function. It's a compositional structure. So you start with the input vector, and you pass the vector through different what are called layers here. And each layer is very simple. It has two pieces. It has an affine piece. An affine piece consists of a weight matrix and what is called a bias vector. And then this output of this affine layer is passed into a scalar activation function, just a very simple scalar nonlinearity. So you start with an input, put it through this affine function, compose it with a scalar nonlinearity, another affine function, the same scalar nonlinearity, another affine function, the same scalar nonlinearity, and you keep on doing it, keep on iterating it. So you end up with this. This is a deep neural network. Now, why should it be able to learn functions? Why should it be able to learn the lift and drag of a fluid flow? And the secret to that success partly is that it has tuning parameters. It has these weights and biases. And these have to be determined, these have to be chosen. And the way we do it in what is called supervised learning is, remember that we have this parameter space, which could be high dimensional. We choose a random selection of points, a random training set. This could be random with independent and identically distributed. And on these points, we have to provide the data. We have to provide what is called the ground truth. So the function L, which is my target function, is evaluated at these points, possibly in a noisy manner, but nevertheless, it is there. And now what you're going to do is you're going to find the parameters, the weights and biases of the network, such that the mismatch between the ground truth and the neural network at these points is somehow minimized. And this mismatch can be expressed in terms of an LP norm. It could be 1 or 2, depending on the context. So you end up with a very high dimensional. Remember that these parameters will be in hundreds or thousands of dimensions. These are these matrices and these vectors. And the loss function, this objective function here, this mismatch, is going to be non-convex, highly non-convex in terms of these parameters. So to solve this non-convex, very high dimensional optimization problem, we use a stochastic gradient descent ADAM. There are different ways to do it. But this is supervised learning in a nutshell, that you need to have some data, some ground truth. You need to parameterize your deep neural network, and you need to train it to somehow match the data. That's all that you do. It's a very, very simple process. So it seems simple. Nevertheless, can it be done, right? So remember that my target is to learn a function, not just, and I'm all that I'm given are point values. So in some sense, it's an interpolation problem. And then I want to find a deep neural network such that for a given tolerance, error tolerance, which could be very small, I have a neural network that is close to this, or the error with respect to some suitable norm is going to be small. Can this be done? In principle, yes, because there is the beauty of these deep neural networks is that they have something called the universal approximation property. What is that? So as long as the underlying map is continuous, even just measurability is enough. If it's even measurable, then for any tolerance, any small parameter epsilon, you can find a deep neural network. In fact, you can find a shallow neural network with a single hidden layer, single compositional structure, such that this norm is going to be as small as you desire. So this is a very, very powerful property. The ability to represent, to approximate functions is a very, very powerful property of this class of, special class of functions. And then you can be much more quantitative, because this is a sort of a qualitative result. It doesn't, existence result. It doesn't tell you what is going to be the size of this neural network, how many layers, how many neurons, and so on. This can be made quantitative. For instance, in this paper of Yarotsky, 4 or 5 years back, it has been done. So as long as your function is Sobolev regular, so roughly speaking, it has S derivatives, then this is the explicit quantitative statement. So the error in representing any target function, which is Sobolev regular, is measured in these terms. So what you see from here is that there are two quantities. M is the size of your neural network, and there are two quantities in the exponent here. So you have the dimension, T bar. So this is your parametric dimension, 20, 50, 100, depending on how many dimensions you represent your quantity in. And you see that there is a very bad dependence on dimension, right? If the dimension increases, then clearly this number is going to be very, very large in some sense. But on the other hand, so there is a negative dependence on dimension. There's a positive dependence on regularity. More regular functions, the easier it is to learn them. Unfortunately, the situation that we encounter in scientific computing, the examples that I gave you, flow past an airfoil, or for instance, this kind of turbulent, chaotic fluid flow, the point is that you don't have regularity and you have high dimensions. So your S is small and your D is large. So you get hit by both ends. So at best, you can assume that it is BV, or let's assume that it's Lipschitz continuous, just for the sake of argument. And let's say that this dimension is only 6, and this is a sort of a toy problem if you have only 6 dimensions. Then you can already see that just to get 1% error, 10 to the power minus 2, your network has to have a size of a trillion, something very, very large. So you cannot afford to train such neural networks. And this is because of what is called the curse of dimensionality. Because the size of your neural network to obtain a certain accuracy scales exponentially with respect, or grows exponentially with respect to dimension. And that really is, that's a killer. That doesn't allow you to do proper approximation. So this sounds very, very pessimistic, this sort of worst case guarantees. Unfortunately, or fortunately for us, one can do a little bit more refined error analysis. So it turns out that this error between the neural network and your target function can be decomposed into 3 parts. So let me walk you through these 3 parts. The first part is what is called approximation error. This is just a best approximation. So remember, the neural networks are a hypothesis class, are a space, or a subspace at least, and they have a certain structure. So what is the best approximation in this class? Now, it turns out that as long as you're solving PDEs, now solutions of PDEs have a special structure, then whether it's an elliptic PDE or a parabolic PDE or even nonlinear hyperbolic PDEs, you can prove rigorously that this the approximation error, this best approximation error, scales with dimension. Of course, it grows with dimension, but it has to. However, this is not an exponential dependence. It is a polynomial dependence, and in many cases, this is a linear or a quadratic dependence. So you can do much better than what this negative worst case results indicate. So this is a hopeful result, right? It's positive. So we know that the size only grows polynomially with small polynomials in the dimension. Then there is something called the optimization error. Now, this is very hard to sort of estimate because you're solving this non-convex high-dimensional problem, and there's no guarantee that you will ever get a global minimum. So in practice, you just find it or you approximate it by training error. So during training, a posteriori, you can compute this quantity. So hopefully this can be made small. So you're left with the last piece, something called the generalization error. Now, this is because you are an integral, you are a norm, right? The mismatch was a norm, and you have replaced it by a quadrature. Here, it's sort of just a random Monte Carlo type sampling. Of course, this will lead to an error, and one can use, because there is a lot of dependency, or one has to use some smart arguments, something called concentration inequalities, Hofting's inequality, and the like. And then you obtain an error which scales like this. So it's essentially, remember that central limit theorem tells you that things should be square root in the number of sampling points. The error should be decaying as a square root of the number of sampling points. It's essentially that, except for a logarithmic correction. This is because of correlations. You can estimate this. So at the end of the day, this is a hopeful result because maybe we have small neural networks because we don't have the curse of dimensionality that can approximate my problem. And the training error is small. So my overall error, it behaves essentially like a square root in the number of training samples. Of course, it depends on the size of your neural network. So let's say that this size is order 1. Nevertheless, we still have a problem because now to get 1% error, 10 to the power minus 2, I need 10 to the power 4, 10,000 training samples. Now, 10,000 training samples doesn't seem to be a lot, but and in practice, when you have the traditional problems of machine learning, like face recognition or speech recognition or natural language processing, indeed, that's not a big number. It's cheap to take 10,000 images. However, the setup that we are in, 10,000 simulations, because this data has to come from simulations or from experiments, just imagine doing it 10,000 times. So this itself is almost infeasible. This is impossible because a single simulation is so expensive on a supercomputer. You can imagine how much 10,000 simulations is going to be. So this is not a good statement, even with this refined analysis, because now the challenge is that you have to learn maps of a low regularity in a data poor regime. And this should be contrasted with the standard sort of big data successes of machine learning. So we have to sort of parse this distinction and keep that in mind all the time when we are developing deep learning for PDEs. But what can we do? Now, we can do many things. One thing that we can do is we can use this trick, which is what tells us that our training set should be random. We can, for instance, use special training sets, what are called low discrepancy sequences. Now, these are used heavily in numerical integration and what is called quasi-Monte Carlo integration. And the reason why they're used is because they are better spread out. So just to give you an example, this is a unit square, and I've divided it into small boxes. And you can see that the random points, blue dots here, there are many boxes which don't have a single random point. Whereas these equidistributed sequences, low discrepancy sequences, they are much better distributed because many of these boxes have these points. So they're as easy to generate as random points. Nevertheless, they have this equidistribution property. And because of that, we can prove rigorously, and this is done in this couple of papers here, that the total error now scales as a training error. Remember that this is, you can't touch it, you can't really estimate it. And then it scales not like 1 over square root of n, but because of the special structure of these points, it scales linearly, 1 over n. Of course, there's a logarithmic correction, which depends on the dimension. So this has to be kept in mind. But 1 over n is much better than 1 over square root of n, right? If this were true, then we only need 100 training samples and not 10,000 training samples. In fact, you can do even better. If your target function is complex analytic or real analytic, let's say holomorphic in a suitable sense that I don't have the time to go into, and typically solutions of elliptic and parabolic PDEs with the right kind of initial or boundary data have this kind of structure, then we have some special low discrepancy sequences where the decay is even quadratic. So it decays very, very fast with dimension. And using these as training points makes the problem much more feasible, much more tractable. So now we use some of these tricks. There are many others that I don't have the time to tell you today. I'll give you some examples to illustrate the power of these methods. The first example we want to predict. So what we want to predict is, given the shape of the airfoil, remember it is parameterized by the 6 Henne parameters, in this case 20 of them. We have a compressible flow around it, transonic compressible flow, and we want to predict things like the lift and the drag, and in some cases we want to predict the whole flow field, the steady flow field. And you can see that just visually it's a very, very good prediction. And this is also borne out by the quantitative information that's put on this table. So my deep neural networks are relatively small. I have about 10,000 to 10,000 parameters, so not a very big network. I have 128 training samples. So this is sort of the gold standard here. And to generate a single sample could take me something like the order of minutes, like 40 minutes for this very highly resolved simulation. On the other hand, to evaluate the lift and the drag with a neural network is taking me 10 to the power minus 5 seconds, like a microsecond, right? So this is like 9 orders of magnitude. And you can see that the error is about 1 to 2%. Even for the whole field, where I have to evaluate the field at several points, 40,000 points in this particular instance, still it takes about 1/10 of a second, whereas the simulation was 40 minutes. So you still have 3 to 4 orders of magnitude speed up, right? Even with shocks and so on in your flow field. And the error is about 1 to 2%. So this is a very satisfactory situation. And this is one example of the power of these methods. And we can deploy them for applications. For instance, we can do not just prediction, but uncertainty quantification. Uncertainty quantification is that you want to compute statistical quantities. So for instance, you want to compute the whole histogram, the probability density function of the lift and the drag. And you can see that these are almost indistinguishable from the ground truth. And when we do a fair comparison with the state of the art, which is quasi-Monte Carlo, you still get a factor of 7 to 9 speed up, an order of magnitude speed up. Over Monte Carlo, it's 2 orders of magnitude speed up. And there's another trick that I didn't have time to discuss with today, multi-level training, then you get something, another factor of 5. So at the end of the day, you have something like a factor of 30 to 50 speed up on these problems, which is impressive. Another thing that you can do is to do PDE constraint optimization. So you not only want to predict, but you want to optimize. You want to optimize the shape of the airfoil such that the drag is minimized at constant lift. And with these shapes, you can see that we have 50% reduction of the drag. But now with an active learning algorithm, which I don't have time to describe today, you have to learn the training set instead of fixing it a priori as random points or sobol points. You learn it on the fly, you learn it during the computation. You again can get a factor of 30 speed up. So this is the main point. So on these kind of problems, you do see a speed up, a significant speed up over what can be called as the state of the art. So it's really successful. And a final example, tsunami simulations. This is in the Mediterranean Sea, but the same considerations apply to tsunami simulations in the Indian Ocean, for instance. So you start with an earthquake and you want to predict the tsunami, what is the wave height, what is the arrival time, different observables. And the way it is done is that you solve what is called the shallow water equations. And there is a model by which the deformation of the seafloor due to the earthquake is translated into initial conditions for the simulation. It's called the Okada model. It has 9 parameters. And then the state of the art, which is also done in my group, together with uncertainty quantification, takes about an hour for the Mediterranean. It takes longer for the Indian Ocean. So what do you do in that case? You train deep neural networks with the arguments or with the techniques that I just presented. And here you're interested in discrete locations, what are called buoys. So I focus here on the coast of Italy, on Puglia, different locations on Puglia, one Basilicata, and you can see that the time series is very, very accurately resolved by the deep neural network. Even the worst prediction that we have, this absolutely the worst prediction, is still very good. As you can see, it's very close to the ground truth, to the reality. So now, this entire simulation took again a fraction of a second, 1/10 of a second. So from 60 minutes to 1/10 of a second, it's a big 2-3 order gain of 2-3 orders of magnitude. So these kind of problems, they really work once you, or methods, they rather really work once you do it properly. But now the rest of my talk, I will also talk about some drawbacks of these methods and some future improvements, right? So to sort of set the stage, let me recall that we have this high-dimensional parametric PDE, right? We have these parameters, shape, or the Okada parameters to produce the initial deformation. And the point is, for these many query problems to do deep learning, I needed many ingredients in it, right? So one thing is I needed the PDE. I needed exactly to know the PDE, because otherwise, how would we do the simulations, right? Also, we needed, and this is the serious one, we really needed to know there's an underlying measure on the function space. And we needed to know this, to prepare the parameterization. Someone has done the parameterization with the Higgs-NF functions or with the Okada parameters, and this required a lot of expert knowledge, right? And finally, we also required a convergent numerical discretization. Otherwise, how would we generate the data? Now, unfortunately, in reality, these yardsticks, they're not met. Because you could have missing physics, you could have incomplete physics, you don't know your entire PDE, maybe there are some coefficients that you don't know, some forcing terms that you don't know. The data is not necessarily acquired from just some numerical simulations, but also from experiments, from observations, which means that they're subjected to measurement noise. And the most serious thing is that in practice, you don't know this measure, right? You get some observations, you get some experiments, you don't necessarily know this measure. You only know some samples from this measure. So to prepare these parametrizations is not so easy, right? And this is what is the big problem here. You don't know how to design these good parametrizations. And also your surrogates are resolution dependent because they were trained on data that was resolution dependent. And there is some issue of out of distribution evaluations that I will come to at the end. So because of all these problems, we have to double back a little bit, go back to the drawing board as it were, and think what is necessary. And soon you come up with the answer. The answer is you can't just learn functions. You actually have to learn operators. And the rest of my talk will be about operator learning. So what is operator learning? Remember that at a very abstract level, a PDE has this formula. A differential operator acting on a function gives you another function, roughly speaking, right? So given this function, the right-hand side, the inputs to your PDE, the solution operator somehow inverts this differential operator, roughly speaking, right? So given a U, the inputs to a PDE, which are functions, we produce another function, which is the solution to the PDE. So the underlying solution operator for a PDE is an operator. It's a mapping between an infinite dimensional input space and an infinite dimensional output space, function to a function. So far, what we have done is that we have taken a vector, a finite dimensional object, and produced a vector, another finite dimensional object. So now in PDEs, on the other hand, at the bottom, what you have are operators, mapping between function spaces, infinite dimensional function spaces. And what we should be doing is to sort of approximate the solution operator from data, right? Given data, we should be able to approximate the solution operator, and learning this operator instead of functions is what is called operator learning. And there are different ways to different paradigms, different frameworks for operator learning. In my talk today, I will discuss a very recently proposed paradigm, something called deep operator nets or DeepOnets. So let's start with what are DeepOnets. Their lineage, the ancestry goes back to operator networks, which were proposed already by two Chinese scientists, Chen and Chen, in the 1990s. But very recently, George Kaniadakis and his group at Brown University in the US, they sort of rejuvenated this approach. They made it deep because they added more hidden layers, and they came out with this name, DeepOnets, christened it as DeepOnets. So let me try to explain what a DeepOnet is. Recall that my input is a function and my output is also going to be a function. So what we're going to do is in a DeepOnet, your input is a function. Of course, on a computer, we have to only take finite approximations. We can't put in a continuum. So we evaluate this function at points. It could be also local averages or testing against a test function locally. And this is one step. Then this is just a finite dimensional object, which we put into a neural network. Remember, neural networks can take finite dimensional vectors and they map onto vectors. So this is what is called a branch net. So this is a neural network. And on the output side, remember, we also need to produce a function at the output side, right? So the output side, given your output space, output domain, this could be a point, you take or a vector in the output space, you take another neural network, something called a trunk net, and you produce a neural network out of it. So, and you combine them in a linear and affine manner. So here is the final formula. So what you do in this case essentially is that the trunk net is like a basis for expressing the operator in the output space. So these are functions, whereas a branch net provides coefficients for these functions. And together they're supposed to approximate the operator. And this has been very, very successful in numerical experiments already, even though it has only been proposed, let's say last year. And why is this so successful? Means why do they work, this kind of approaches? So at the root of it, just like, so remember, now we're dealing with infinite dimensional objects. We don't have necessarily finite dimensional objects. And it was Chen and Chen already had produced a universal approximation theorem, proved a universal approximation theorem. Remember that for finite dimensional neural networks, we had a universal approximation theorem. And it is very similar here for the infinite dimensional neural networks too. So, for DeepOnets. So the theorem is like this. As long as you have a continuous operator mapping from a compact set, a compact subspace of continuous functions onto continuous functions, this can be relaxed. You would have some other LP functions here. But the key thing is continuous operators on compact sets, then there exists a DeepOnet which can approximate it to the desired precision. So this is a framework here. But remember that compactness is a very serious assumption, right? It's essentially making things finite dimensional. And in practice, you cannot rely on using compact input spaces. G also can be discontinuous. So this is a limitation for this theorem. So certainly it doesn't explain why it does so well in numerical experiments. And again, this is a qualitative result. It's an existence result. So you don't have any quantitative information on how many sensor points, these evaluation points that you need. What is the size of this trunk net? What is the size of this branch net? These questions are not necessarily answered in this framework. And remember that the underlying task is infinite dimensional. So already in the beginning, I told you that with finite dimensions, you have a curse of dimensionality. What happens for an infinite dimensional problem, right? So it wouldn't be very strange to expect that the size of your DeepOnet would depend exponentially on your accuracy. So you'll see that indeed happens, that if you make things smaller and smaller, because it's an infinite dimensional problem, the size of your DeepOnet is going to expand and it's going to blow up. So operator approximation, because you have an underlying infinite dimensional space, could easily be marred by the curse of dimensionality. So this is not enough. So we have to somehow remove these limitations, as it were. And this is done in this very long paper, very recent paper with my PhD student Samuel Lanthaler and with George Kaniatakis from Brown University. So we proved several results, and I will take the next 10 minutes to sort of walk you through some of these results. The first is, remember that we want to remove this compactness assumption on the input spaces, and this is not hard, because in a way, if you think about it, we have to train the neural network, right? We have to train the DeepOnet. To train it, we have to take samples. Earlier, this was random points in a finite dimensional space. Now there is infinite dimensional space. So what we have to do is we still have to sample randomly. So what we do is you have to have a probability measure on the infinite dimensional space. This has to exist. And you can sample out of it independently and identically distributed. Sorry. And then what you do is for each of these samples, you have the ground truth by measurements, by simulations, by experiments. And then you minimize the effect, exactly as before, typical supervised learning. But this kind of a training suggests the following definition of error, or generalization error, as it were, that you have this mismatch between the underlying operator and your DeepOnet. This mismatch, of course, has to be normed in space. But in function space, because you're doing it over a function space, you have to integrate it in L2 for convenience, but this can be an LELP norm. You have to integrate it against a reference measure or against the underlying measure. So this is the definition. So your problem is actually you have not just an input operator, but you also have a measure. And in infinite dimensions, there is no canonical measure. Not everything is a Lebesgue. There is no Lebesgue measure, right? There is no canonical measure. So now what we did in this paper is we were able to prove that in this setup, as long as you have a probability measure on your function space, and as long as your mapping is just a mapping, it has to be a measurable mapping between L2 to L2 or LP to LP for that matter, then the DeepOnet is going to approximate your underlying operator. So this has exactly the same sort of universal approximations properties that finite dimensional neural networks has. That's miraculous, right? So we have a construction that can approximate operators, infinite dimensional objects in a very generic manner. So that's the first thing. And it also reveals a key role for this measure, for this input measure. It has to be there, right? This is a reasonable assumption. But of course, this does not still give you quantitative information. This is what you want. And to get this, we have to sort of revisit or review DeepOnets. And we think of them in the workflow in the following three phases. Best to illustrate it in this sort of commutative diagram. So you have an operator which takes an infinite dimensional input X and maps to an infinite dimensional output Y. So now what a DeepOnet does is that it goes through these three steps. So first it does an encoding, which is it samples an infinite dimensional function in a finite number of points. So this is an encoding. Then it passes things through a finite dimensional step, maps possibly high finite dimensions to high finite dimensions, but nevertheless, it's a finite dimensional neural network. And finally, it has to map back into infinite dimensions. And this is done through what we call a reconstruction, but it's, as you can see, it's essentially fitting coefficients to the trunk net. So it's not a surprise that your total error is decomposed as errors of each of these three pieces, because this is just a composition. Now, what we do is that we are able to control errors in each of these components. And let me very quickly tell you how it is done. So first, we start with the reconstruction error. And this is essentially, this is a projection onto a affine subspace or a linear subspace. So one can use what is called principal component analysis. One has to work a little bit. And then you prove both upper bounds as well as, very surprisingly, lower bounds. Let us look at them. So the key role here is played by what is called the covariance operator of your underlying measure. So you have a push forward measure, you have an underlying measure, you have an operator, this pushes forward your measure. And with respect to it, you can always define a covariance operator. And how fast or how slow the eigenvalues of this covariance operator decay tell you how big or how small the error is going to be. In addition, remember that my trunk net is just a neural network. It's not the eigenfunction of your covariance operator of the push forward measure. So this has to also approximate the eigenfunctions. So that contributes to the error. So now you can see that the action of the measure together with the operator determine how fast your error is going to be decaying, and also brings out a limitation. Means if this goes slowly, then you can't do anything because there's a lower bound. So both ways you have quantitative information. The second point is encoding error. Again, remember that you are sampling at points, but since these are linear spaces, you can do a PCA on the input space. Now the operator plays no role. The covariance operator is defined completely with respect to the input measure. So if it decays fast, then your error is going to be small. Of course, there is some issue that we are doing point-wise evaluations rather than computing sort of an orthonormal basis, right? So since we're doing point-wise evaluations, we have another source of error, something called aliasing error, which comes from essentially spectral methods. So to remove that, we were also able to prove, and I'm really proud of this, that if you choose these points randomly, means how are you going to choose these evaluation points? Random points are almost optimal. They're not completely optimal, but they're almost optimal, which is a big advantage of this. So that was the story of the encoding error. And the final bit is this finite dimensional piece. So remember the commutative diagram. So now you want to compare this map with some other projection of the infinite dimensional operator onto this finite dimensional spaces, which is done with these projection operators. And this is a traditional neural network approximation problem. And here lies the problem, right? Because then, as before, the size of the neural network depends on your regularity. So somehow you have to understand the regularity of this projection. It also depends on the number of sensor points, because that's your dimension now, right? This RM is your dimension. It's a number of sensor points. But this is a problem, right? Because remember that the number of sensor points was necessary to control the encoding error. If you want this encoding error to go to 0, depending on how fast these guys decay, you still need infinite number of points, unless until you have a finite dimensional problem, right? So you need infinite number of points. As epsilon goes to 0, m, the number of sensor points goes to infinity, and your total size goes, epsilon goes to 0, so it's a 1 over epsilon, but an exponentiated onto another quantity which goes to infinity. So this is like a double exponential, a super exponential dependence. And this tells you that a priori, you cannot rule out the curse of dimensionality. In fact, it should be marred by the curse of dimensionality. Then you have to be smart. Remember, just like we did in the finite dimensional case, you have to appeal to the structure of your PDE. And depending on the PDE, you can use different kinds of structure. I don't have a lot of time, but very briefly, if you have elliptic PDEs, for instance, this one here, elliptic PDE, the operator is a mapping between the coefficient, which is your input function, and the solution, which is your output function. Then one can prove that this mapping somehow is, you can prove that the projection is going to be holomorphic in a suitable sense. And then, of course, the size of this doesn't grow exponentially. In fact, it grows logarithmically, at best logarithmically. And formally, you can see that if analytic function, so this k goes to infinity. So this guy goes to infinity, this guy goes to infinity, there is some chance to control them. And it is some work to make this rigorous, but in these problems, we can prove that the size, far from going exponentially, actually grows at most logarithmically in terms of the accuracy. So there is no curse of dimensionality here for elliptic problems, for instance. Now for parabolic and hyperbolic problems, we have to use, my apologies here, we have to use a different technique, a completely different technique, which is to emulate numerical methods. Again, maybe I very quickly go through it. So you have an elliptic PDE, and now the operator is a mapping between your right-hand side and your solution. For those who know finite elements, this is the finite element method. It's just you evaluate the right-hand side on quadrature points, you form the stiffness matrix, you invert the stiffness matrix, and finally, you use the finite element space to represent the approximation. Now, it turns out the DeepOnets will trivially emulate this, right? Because the sensor points can be your quadrature points. The branch net is just a linear map. Linear functions are, of course, approximated by deep neural networks. And trunk nets only need to approximate the finite element basis functions. So here is finite elements represented in terms of DeepOnets. So if you can do finite elements, you can do spectral methods, you can do finite volume, you can do finite difference, and so on. And by doing this for the parabolic PDEs, nonlinear parabolic PDEs, so-called Allen-Kahn equations, and nonlinear hyperbolic PDEs, we are also able to prove that the growth is not going to be exponential. It is going to be polynomial with some small polynomials. And because we have these lower bounds, we almost have some optimality results. For instance, for hyperbolic conservation law in 1D, we proved that the DeepOnet error scales as the number of trunk nets, roughly speaking, 1 over p. That's the worst that you can do, or the best you can do, sorry. And the worst you can do is very close to the best you can do. So you can almost optimally represent them using DeepOnets, which is a very nice result. Now, I don't have a lot of time to discuss numerical results, but very simple example. So this is just a pendulum, ODE, but nevertheless an interesting infinite dimensional problem in that sense, because my input is a function, right? And my output, the displacement, is also a function. So here is the input, and here's the output. And what I do is I train on Gaussian random fields. So these are very special. The measure is a law of a Gaussian random field. And I use very small networks. And you see that the mean error is just 0.7%. Very, very accurate prediction. And another big, there are some other numerical results that I skip here. But there are some, one thing which is very nice is, remember that in a parametric setting, everything has to be parametrized. So if it's just outside the parametric setting, you can't even evaluate. Here, on the other hand, since we have functions, we can do whatever we want, right? So I train on a Gaussian random field, but I evaluate on Chebyshev polynomials, which are not necessarily Gaussian random fields. They look a little bit, when the degree is 5, they look a little bit like Gaussian random fields. So you have very, very small errors. It's like 0.4%. But then I make them more oscillatory. For instance, I take Chebyshev polynomials of degree 10, and you can evaluate it. It means it's not going to be very accurate, but you can evaluate it. In fact, it's not so bad. The training process has never seen a Chebyshev polynomial of degree 10, yet it makes an error of only 3 or 4%. So these are very satisfactory. So you can do this kind of out of distribution, because now the distribution was Gaussian random fields, but our evaluation is done out of distribution. So these are some big advantages of these methods. So this brings me to the close. So as I said, my interest was in learning high-dimensional PDEs with deep neural networks. And these problems arise in many practical situations. And I showed you different kinds of techniques. One is with the standard supervised learning for parametric PDEs. But in many, many cases, you can't parameterize. Then you need operator learning. And I illustrated DeepOnets, but there are also other operator learning frameworks. For instance, something called Fourier neural operators. We have a paper out on that soon. And what I did not talk about today is high-dimensional state spaces. So the physical dimension itself is 100 or 10 or 20 or whatever. This requires different techniques, and this is for another day. But the main point is that this is not your black box machine learning algorithms, which are there in computer science. You need a significant amount of innovation to apply these techniques successfully in the context that we are interested in. So thank you very much for your attention.